a gente vai começar então as palestras, né, da pós-graduação. Eu tenho o prazer de convidar o Dr. Roberto Budzinski. Eu vou ler o seu livro. Tá? Ele é bacharel, mestre e doutor aqui da Universidade Federal do Canadá. Atualmente é pós-doutorado na Western University Fields Institute, Canadá. Sua pesquisa integra dinâmica não linear, teoria de redes, neurociência, neurociência computacional e aprendizagem de máquina. Dr. Budzinski, ele desenvolveu uma nova abordagem que vincula o espectro de uma rede oscilatória à sua dinâmica emergente, oferecendo insights analíticos sobre fenômenos como sincronização, ondas viajantes e estados quimerais. Seus interesses atuais se concentram em dinâmica transiente, emergência de ondas em redes neurais, computação baseada em dinâmica e abordagens matemáticas para aprendizagem de máquinas. Então, eu deixo a palavra para o professor.
Obrigado. Obrigado, pessoal, pelo convite, por estarem aqui. É um prazer estar aqui, como foi falado, eu fiz minha graduação, meu mestrado e meu doutorado na universidade, nesse programa. Então é muito legal estar de volta aqui para mostrar um pouco da pesquisa que eu tenho desenvolvido no meu pós-doutorado no Canadá. Eu não sei quantos de vocês estavam aqui na sexta-feira no workshop, eu apresentei no workshop aqui também. Então, metade dessa apresentação eu já mostrei na sexta-feira e a outra metade é coisa nova. Então, para os que estavam aqui na sexta, vai ter coisa nova também. E no meio da apresentação, se vocês tiverem dúvida, não precisa guardar as perguntas para o final. Pode levantar a mão, perguntar, que aí a gente vai discutindo, que eu acho que fica mais fácil assim. Então, fica à vontade, só levanta a mão e aí a gente consegue discutir. Então, eu fiz meu doutorado aqui na UFR, e no grupo do professor Viana, do professor Thiago, do professor Sérgio. Então, meu doutorado foi em dinâmica não linear. Eu estudei redes de neurônios, spiking neurons, não as redes de machine learning, mas as redes mais voltadas à neurociência computacional. Agora, eu estou na Western University, a gente está no departamento de matemática, mas a nossa pesquisa é um pouco de matemática aplicada, neurociência computacional, e agora a gente está fazendo uma transição também para machine learning. E recentemente, o meu supervisor, agora ele virou diretor de um centro do Fields Institute de matemática. Eles criaram um centro novo para a ciência de network science, então agora a gente também faz parte disso. E o que eu vou mostrar para você aqui é a parte da teoria que a gente está desenvolvendo, porque a nossa pesquisa ela integra, a gente tem gente fazendo experimentos em neurociência, a gente tem pessoal fazendo pesquisa muito mais aplicada a machine learning propriamente dita, e o que eu vou mostrar para vocês aqui é a teoria que a gente está desenvolvendo para tentar vincular essas duas coisas e explicar os fenômenos que a gente observa em neurociência e em machine learning, mas eu também vou mostrar um pouco da aplicação que isso tem. Então, quando vocês verem esse resultado, mantenha na cabeça que a gente também tem experimentos acontecendo sobre isso e tem outras linhas também sendo desenvolvidas. Então, só para dar um overview da minha pesquisa, isso, quando eu falo minha pesquisa, basicamente essa é a parte que eu estou liderando da pesquisa lá, mas tem muita gente no nosso grupo e colaboradores que também estão trabalhando nisso, e então não é só minha, né? Mas a ideia geral, imagina que a gente tem uma rede. Então, cada ponto aqui representa um nodo nessa rede, por exemplo, pode ser um neurônio de uma rede neural, ou pode ser uma população local de vários neurônios, ou pode ser um nodo abstrato, tem uma dinâmica individual. E para a gente o que é importante aqui é que esses nodos eles estão acoplados, então a gente tem uma rede. E a pergunta que a gente tem é a seguinte: essa rede está acoplada de uma certa forma, a gente tem a dinâmica individual acontecendo, como que numa rede, mesmo quando as conexões são simples e a dinâmica individual é muito simples, pode acontecer um fenômeno que a gente chama de dinâmica emergente, e aí o que a gente tem são essas, quando a gente olha o coletivo da dinâmica, é muito mais complicado do que essa dinâmica individual. Mesmo se você somar essa dinâmica individual, ela não é tão complicada quanto a dinâmica que resulta da interação entre esses nodos. Então, a pergunta que guia a nossa pesquisa é: como que a conectividade dessa rede ela dá suporte para essa dinâmica aparecer? E por que a gente está interessado nisso? Porque do ponto de vista de neurociência, hoje em dia a gente consegue mapear as conexões no cérebro. Isso pode ser a tanto nível numa rede, por exemplo, você pega um pedaço do córtex, a gente consegue medir as sinapses que existem lá. Aqui, por exemplo, é na escala do córtex inteiro. Essas são as fibras que conectam diferentes partes do córtex. Então, hoje em dia, a gente consegue medir isso. Esse foi um grande paper que saiu em 2008, então, muito tempo atrás. Hoje a tecnologia está bem avançada. A gente consegue medir toda essa, com grande detalhe, toda essa conectividade em sistemas neurais. Ao mesmo tempo, a gente consegue medir a atividade que existem nesses sistemas neurais. Então, esse é um trabalho do meu supervisor na época do pós-doutorado dele. Esse aqui é um dado, isso aqui é dado real, isso aqui é de pacientes humanos que têm epilepsia, e muitos desses pacientes, eles precisam, a gente precisa monitorar a atividade neural deles para entender como que as seizures acontecem. E essa seizure, ela precisa acontecer espontaneamente. Então, o que acontece é que o paciente, às vezes, precisa ficar 2 semanas no hospital com os implantes até que essa seizure aconteça. Então, antes que a seizure aconteça, a gente consegue medir toda essa atividade. Então, 24/7 a gente está medindo essa atividade, e aí a gente consegue fazer diferentes, por exemplo, teste de memória, teste de atenção e assim por diante. Então, o resultado que eu vou mostrar para vocês aqui é um resultado de um cérebro humano, e aqui cada ponto representa um eletrodo na superfície do cérebro. Então, o vermelho é o ponto, é a linha preta lá, os outros estão em cinza. E aqui eu vou plotar essa atividade normalizada, mas eu não tô fazendo nenhum tratamento de smoothing aqui. Essa é a atividade que a gente vê. Então, normalmente, a gente pensa no cérebro como sendo uma coisa meio aleatória, tem várias coisas acontecendo ao mesmo tempo. Entretanto, existem esses comportamentos que, claramente, isso aqui é organizado. Isso aqui é uma onda espiral. Enquanto o cérebro está nessa oscilação, a gente vê que a amplitude vai para cima e vai para baixo. Isso acontece em estágios do sono, isso é chamado de sleep spindle. E aí, uma das coisas que a gente está investigando é que esse tipo de comportamento está ligado à plasticidade que acontece durante o sono. Então, assim, essa dinâmica aqui está longe de ser aleatória. Ela é bem organizada e é organizada da forma de uma onda. Então, a pergunta que a gente tem é, como que a conectividade no cérebro possibilita esse tipo de dinâmica para acontecer? Isso, na verdade, é ECOG, então o EEG ele é externo, né, no crânio. Esse, como precisava de precisava ser um pouco mais preciso, então esse eles retiraram parte do crânio, e os dados, os eletrodos vão na superfície do córtex, e aqui são 64 canais, mas 32, desculpa, e ele vai só de um lado aqui do cérebro, porque o que acontece? Esses pacientes, como eles estão lá por uma questão clínica de epilepsia, a gente não pode dizer aonde os eletrodos vão. I'm gonna switch to English now. Yeah, so and that's like so this is still happens like this kind of like, it's called ECOG because it's like the electrodes go on the surface of the cortex, and now we have ones that they are depth, so we have like they are introduced in the brain, but we don't have a saying where they will place this because it's a clinical thing. So it's the ethics will never allow us to say put it here because it's because of the health of the patient. But this is just to show you the type of dynamics that we have. So when we are studying traveling waves and synchronization in the brain, it's not just because it's a thing that is easy to study and in a physics perspective. It actually happens and is important for different reasons. And on the other hand, we also have these artificial neural networks. And here, this is just like a toy example to show you. So here we have different layers. This is a video that I will play for you. And this network was trained to identify the digits that we have there. So we can see here that when we have different digits, the pattern of connectivity and activity in this neural network, it changes. And somehow, embedded in this connectivity and this pattern of activity, the network learns how to identify a given digit. So the question that we want to answer is that, what can we say when we look at a pattern of connectivity about the dynamics that will emerge in this network? And further, when we are able to identify these dynamics, what can we do that regarding computations? Can we do computations with this network that we train the connections, and now we know how to predict the dynamics? So those are the questions that we are trying to answer in our research. And so what I will show you today is we have developed a new way to look at oscillator networks, and I will show you this in the beginning. And for those that were here on Friday, this is a part that I already showed. So I kind of like I summarize here, just like with the main things that we have there. And this is more or less an application of this approach. But then I have a lot of applications that we can use. How can we use the spatiotemporal dynamics to perform computations in these networks? And what can we learn from this approach? So just to start, I'm considering one of the basic models that we are studying is called the Kuramoto model. So the Kuramoto model was originally introduced as a model in physics to study oscillations. So it's a very, very simple model. And it basically shows us oscillations in a given system. So usually if the coupling is low, the oscillators keep oscillating asynchronously. But as you increase the coupling, we can see sort of like a transition to synchronization. And if the coupling is very strong, we can see that these oscillators are oscillating in phase, and that's what we call phase synchronization. So this is just to give you an idea of what is the behavior that we are studying here. But this kind of model is actually able to reproduce a lot of different oscillatory behavior, and it's kind of like a canonical model to study synchronization in these networks. And importantly, this is also a model that we can use in computational neuroscience to model. So the behavior that I showed you before, that spiral wave, we can use this kind of model to model that behavior and try to understand what is the underlying mechanism. The problem, though, is that usually for the Kuramoto model, to obtain analytical insights to this model, we need to do a trick. We need to consider usually what is called the asymptotic limit or the continuum limit. So we have a network with n nodes. When we have n nodes, we have a finite network. But it's very, very hard to obtain analytical insights when you have a finite network. So usually what we do, we consider that n is going to infinity, and then instead of having a sum and a discrete network, we have a continuum network. This sum becomes an integral. We have now distribution functions describing the network, and then we can get analytical descriptions in some cases. The problem, though, is that when we look at a trained neural network, for instance, it's far from being n going to infinity. We have a very specific, it's an individual network that is performing that thing. So in order to understand what is the role of this individual pattern of connectivity, we need to keep the network finite. So we developed this new approach to study the networks in this finite case. So just to give you an idea what we are doing here, what we are doing there, this is the model that we have. This is the Kuramoto model. And here I'm just expressing the Kuramoto model in the case with delays, but our approach works with and without delays. So here the model is very simple. We have a differential equation for the phase. So this is the phase that is between minus pi and pi. It doesn't matter. You can define it's 2 pi periodic, right? This is the natural frequency. So what is the frequency that oscillator would oscillate if that oscillator was not coupled to the others? And this is the coupling term. So here we have a coupling strength that is just scaling the coupling between these oscillators. And as I said, we are interested in finite networks. So we have a sum here. We have n nodes. And this matrix A, here I'm just representing the element of this matrix, but this is the adjacency matrix. So this is describing who is connected to whom. So this could be binary. 1 is if it's connected, 0 if it's not connected, but it can also be weighted, for instance, in the k with distance. And here we have a sign coupling. So we have like theta j and theta I, the oscillators that are coupled. And here in this case, I considered the presence of time delays, and specifically distance-dependent time delays. But as I said, our approach works with or without time delays. And that's one of the main advantages. Usually with time delays, it's very complicated to obtain analytical insights. But in our approach, it's straightforward to get that.
Is it necessary to assume that you have the same natural frequency for
That's a good point. No, it's not necessarily. I will keep it the same now because I want to get a very nice geometric interpretation. But the whole idea holds up even when the natural frequencies are not the same. And that's a good point, because when you go to the brain, not all parts of the brain are oscillating with the same frequency. So that's a good point. So everything that I will show you here it generalizes to the heterogeneous case, but I will show the homogeneous case first because there is a very neat interpretation there. So in this case, the interpretation of the time delay is very simple. The greater the distance between two nodes, the longer it will take for the information to travel from one point to the other. Why am I considering the distance-dependent case? Because that's how it happens in the brain. The further away are two parts of the brain, the greater, the longer it takes for the information to travel there. And there is a neat approximation that I can use in this case, that I can switch time delays for phase delays. And of course, this is an approximation, so it won't work in all cases. But this is basically working when the coupling is not too strong, and the time delays are comparable with the natural frequency of oscillations. So this is basically the case that we have in neural networks, in neural systems. And in this case, this phase delay is just given by the natural frequency times the time delay. So it's basically you're assuming that there is this, you are interpolating from one point to the other, that is the time that it takes for that oscillation to travel. So the contribution that we had in this field, and here I'm summarizing, and we can discuss in detail at any point if you want. So this is, those are differential equations, and usually we need to solve them numerically. So we put in the computer, and we numerically integrate them. We found a way to describe the same dynamics using two operators. So now we are using a lot of linear algebra because we want to gain insights about the role of the matrices there. And what matrices am I interested? The adjacency matrix, because it determines the connectivity, and also the matrix of delays. So this is exactly the question that I had in the beginning. That's why I'm trying to represent the dynamics using this operator, using this matrix operations there. So that's the way that we found a complex valued system that is able to reproduce the trajectories of these Kuramoto networks using two operators. So here I have x, which x is now a complex number. Remember that the Kuramoto model was described in the real numbers. It was just a phase. So now x has amplitude and phase. And what I'm doing here, I am doing a discrete evolution of my system. So I'm going from time t to time t plus var sigma. And then in this time, I'm evolving my system. So I have the previous condition, so at time t, and now I'm evolving for var sigma. That's the period of time that I'm using there. And here I have a matrix exponential. So here I have var sigma times this matrix k, and this matrix k has all the information that is important in the Kuramoto model. So the coupling strength, the phase delay or the time delay there specifically, and the connectivity through the adjacency matrix. So of course, there is a lot of linear algebra to get to this case. And if you don't trust me, you can check the reference. These two systems are exactly the same when I use these two operators. So I can use this to reproduce the dynamics of the Kuramoto model. And then the second operator, so the first operator that I need is the matrix exponential. So the matrix exponential is rotating the oscillators in the complex plane and expanding them or contracting them, so changing their amplitude. But then I need to put a second operator that is my operator lambda. So what the operator lambda is doing is taking these complex values in the complex plane. So the matrix exponential is rotating them, expanding and contracting them. What the lambda operator is doing is putting them back in the unit circle. So is normalizing them. So the tricky thing is this lambda operator is nonlinear because I need to be element-wise and it's changing over time. So this is not giving us an analytical solution for the system. It's not a closed form solution. But the important thing here is the following. The matrix exponential is the only one that is changing the phase of these oscillators because the lambda operator is not changing the phase, it's just changing the amplitude. So the key point here is that by using these two operators, I can interpret the dynamics of the system directly through the eigenvalues and eigenvectors of this matrix K. And why is this important? Because this matrix K has all the information that is important for the Kuramoto network. And that's what I will use to gain the analytical insights and analytical predictions for finite networks. So as I said, it's doable to get analytical predictions for networks that are in the continuum limit. For finite networks, it's trickier. And with this approach, we have shown that we can actually obtain analytical predictions for the dynamics, even in the case with time delays.
Does A needs to be symmetrical?
So no, I will show first the case that A is circulant, but it doesn't need to be because I can always get the eigenvalues and eigenvectors numerically, and the interpretation is still the same. I will first consider the case when A is circulant because there is an expression to get eigenvectors and eigenvalues of any circulant matrix in a closed form solution. So there are two equations to get eigenvalues and eigenvectors for that specific matrix. And that's why the interpretation is very neat there. That's why I was saying that I consider first the case with homogeneous natural frequency to get this case. But the interpretation, it holds up if the matrix is random, still works, but I need to get the eigenvalues and eigenvectors numerically. That's the balance there. Not necessarily, because this is complex actually. This matrix K is complex valued. And so you can always get, and that's actually, I'm saying as it's a trivial thing, it's not. Like we found that getting eigenvectors of complex valued matrix numerically, it's not a very trivial thing, and not a lot of softwares do that in a nice way. But the interpretation of the theory, it works numerically in some cases. It might be tricky to get eigenvalues, and eigenvalues are fine. Eigenvectors is usually a problem. And yeah, we talked to some people that do numerical algebra, and they seem to be shocked with this case that not a lot of softwares can get a lot of good eigenvectors for this case. But the interpretation of the theory holds up. So let me just give you an idea what we can do with that, and then I think it will be more clear that it can be any case. So just to show you, this is the dynamics of the Kuramoto model. So I take that equation that I showed in the beginning, and I integrate numerically. So here is time, here is the position of the node, and in color code, I have the phase between minus pi and pi. So the network starts in random initial conditions, and then it transitions to synchrony that are represented by these horizontal lines, because it means that all oscillators have the same phase for a given time. If I use the two operators in the complex valued approach, and I start with the same initial conditions, I get the same trajectories. Even the microscopic details are there. Cool, so we have a different way to get the trajectories of the Kuramoto model. Why is that important? I will show you why. So this is the complex valued approach. Again, we have the nonlinear operator and the matrix exponential. So when this matrix here is circulant, and what does it mean a matrix to be circulant? So a circulant matrix is where you have a generating vector, and then you just permutate the entries of this vector to get the other rows of your matrix. So in this case, it will be, what is it called, symmetric, right? And so for instance, a type of circulant matrix. Let's say that each node is connected to two neighbors to the right and two neighbors to the left. So the adjacency matrix will be these diagonal lines in your matrix, right? So this is a circulant matrix. That's a very simple one. If all oscillators are connected to all other oscillators, this is called a complete graph. This is also a circulant matrix. But you can have even more sophisticated things. For instance, let's say that the connectivity is decaying with the distance. So this will be a weighted matrix, but it's still circulant because the distance is always the same if you have the periodic boundary condition. So even though it's a weighted matrix, it's still circulant. And why do I care about circulant matrices? As I said, there is a way to get the eigenvalues and eigenvectors analytically. And the eigenvectors are very important here because the eigenvectors of all circulant matrices are always the same. And the first eigenvector is always the eigenvector 1, 1, 1, 1, 1. What our approach showed is that the phase or the argument of this eigenvector is predictive of the dynamics of the Kuramoto model in that graph or in that adjacency matrix. So when we take the phase of this eigenvector, we get all zeros because it's all 1, 1, 1, 1. The phase is all zeros. So this is a predictive of phase synchronization. When this eigenvector is the dominant one, the network will transition to phase synchronization. But the other eigenvectors, they represent Fourier modes. So the second eigenvector is the first wave number. Here I'm just representing the circle because my network is in a circle, but this can be, for instance, in a torus or in a sphere or whatever you want that is symmetric, right? So here in this case, the phase is increasing in that direction. The third eigenvector is the second wave number. So the phase is increasing in the same direction, but now we have two periods. And then the other eigenvectors in the other end of the spectrum, they represent the same waves with the same spatial frequency, but opposite directions. So here we have this over-complete Fourier, the argument or the phase of the eigenvectors of any circular matrix represent a discrete Fourier transform. And what our approach shows is that those are solutions for finite networks of Kuramoto oscillators, and we can represent any spatial temporal pattern in these networks as a combination of these fundamental modes. So let me show you an example, what we can do with that. So let's consider a network. This is a circular network. So symmetrical, let's say we have 20 neighbors to the right, 20 neighbors to the left, and we consider no time delays. So the interaction happens exactly without time delays, instantaneously. When we get the eigenvalues of this matrix using that the CDT, the circular theorem, diagonalization theorem, the eigenvalues are purely real in this case, and the dominant eigenvalue in real part is associated with the eigenvector 111. So this predicts that the network without time delays transitions to phase synchronization because the coupling is attractive. And as I showed you in the example in the very beginning, this makes the network to synchronize in phase and everyone is going up and down at the same time. However, when I add distance-dependent time delays, this rotates the eigenvalues in the complex plane, but it doesn't change the eigenvectors because everything is circulant here because the time delays are distance dependent and the connectivity is also, for instance, just neighbors. So what happens is that the solutions, the possible solutions are the same. The solutions that appear are different because the time delays are changing the stability of these solutions. So for instance, the eigenvalue that is associated with synchronization is no longer the dominant, but now is actually negative. So the network no longer transitions to phase synchronization. The dominant eigenvalue now is associated with an eigenvector that represents a wave with a specific spatial frequency. So with this now, given a combination of time delays and connectivity, I can analytically predict the type of wave that emerges in the network. So just to show you an example, let's consider this ring network. So very simple. This is the adjacency matrix. Yellow means the nodes are connected. Blue means the nodes are not connected. So here we have 20 neighbors to the right, 20 neighbors to the left. And this is a representation of a circular matrix, by the way. And in this case, I consider distance-dependent time delays. So the further away the nodes are, the greater is the time delay. So here the delays are represented in color code. Red means the delay is longer. Blue means the delay is shorter. And white means there is no delay because there is no connection. So our approach allows us to go, for the first time, we look at the adjacency matrix, we look at the delay matrix, and we can predict the type of wave that network will show. And this is for finite networks. So in this case, we evaluate the eigenvalues, we evaluate the eigenvectors, we take the leading eigenvalue, take the eigenvector associated with it, take the argument of this eigenvector, and this is the phase of this eigenvector. So this represents a wave going in this direction with a specific spatial frequency. When we run the simulation for the Kuramoto network with delays, this is exactly the dynamics that we see. So now for the first time, we are able to predict the kind of dynamics that will appear just by looking at the connectivity and the time delays. So for instance, let me give you an example that is not circulant. It's random in this case. So let's consider this brain network that we measure experimentally. So those are the fibers connecting these different areas in the brain. We can count the number of fibers, and this gives the weight that is connecting two different brain areas. And then we model each node here as a Kuramoto oscillator. And here we have not only the connection weights, but we also have the length of these fibers. With the length of these fibers, we can calculate the time delays, the distance-dependent time delays. So now, this is our system. This is the adjacency matrix, much more complicated. It's no longer circulant. This is the matrix with time delays. Again, no longer circulant, very complicated. Even in this very sophisticated case, we have our adjacency matrix, we have our delay matrix. We can get the eigenvalues, we can get the eigenvectors, but in this case, we don't have an analytical expression. We need to do it numerically. And then we can take the leading eigenvector, take the phase of this leading eigenvector, and plot the phase of this eigenvector onto the surface of the brain, because we also have the position of these nodes. And that's the leading eigenvector in this case. So our approach is telling us that the combination of this specific matrix with this specific matrix will generate a dynamics that is predicted like this. So here we have a phase offset going in that direction. So this is a predictive of a wave that is traveling in that way. When we run the numerical simulation for the Kuramoto model on this brain network, that's the dynamic that we have. There is a wave traveling exactly in the direction that we predicted by our approach. So this is, again, to the best of my knowledge, this is the first approach that allows you to have analytical predictions for the dynamics in networks that are finite and with multiple time delays. And why we care about that? Because we have a lot of experimental data showing that there are waves that, for instance, they propagate from the back of the brain to the front, and this is associated with memory. We have waves that are spiral, and this is associated with oscillations during sleep. So now we are able to analytically study the conditions that allow this type of dynamics to emerge in the brain. So we can understand the underlying mechanism that is supporting the emergence of this kind of spatiotemporal pattern. So this was the first part, and this was developed in the first 2 years of my postdoc. It was this theoretical approach to finite networks, mainly to study the dynamics that emerge in these finite networks, keeping in mind the applications to neural systems. Now what I will show you is the thing that we are working on mostly in the previous year and this year, is that we are using the analytical insights that we got from that approach, because that approach showed us, oh, if you use a connectivity like this, if you use time delays like that, you allow your network to display this kind of dynamics, these very sophisticated waves. Now we are using this as a guide to design neural networks to perform given tasks that are supported by these spatiotemporal patterns. And this is important because, again, this type of spatiotemporal pattern is actually measured in real biological systems. So we can leverage that now as a guide to develop different types of neural networks, artificial neural networks now, to perform the tasks that we are interested in. So the first example that I want to show you, it's we developed a neural network to study computations in the visual system. So here, let's say we have a visual input, so an image, and this input arrives to the visual system. Of course, this is a very simplified way of seeing it. In the real one, we have the retina that sends to V1, and then so on and so forth. We have all these higher orders in the visual cortex, and a lot of things are happening there. Of course, this is a theoretical approach, so we are simplifying with the key details there. But what is important here is that we have this picture there. This is projecting to this recurrent network in the visual cortex, and we also have the recurrent connections in the visual cortex. Importantly, these recurrent connections, they decay with distance. So it's very similar to the case that I was studying under a physics perspective. Now I can apply these insights to understand this biological network. So just to give you an example, let's say I have this image. I apply this with feed-forward connections to my recurrent network. And then, of course, I have the imprint of my input, but I also have the activity that is generated by these recurrent connections. because when the input is arriving here, this node is interacting with the other nodes there. So it's not just a simple imprint of the input, but it's a combination of the input plus the recurrency that is happening there. So with that, we are able to train this network to perform predictions of videos. So how we do that? This is a video that I will show you in a bit. So this is a point that is moving around in this 2D plane. So this is my input. So now instead of having just one figure, I have one figure for each time, for each step of time. So this thing is moving, and then this being inputted to the recurrent network. And then in the recurrent network, the connectivities are decaying with distance, and the time delays are also increasing with distance, in the same way that we measure in real portions of the cortex. And then, so this is my recurrent layer, this is my input, and then I have a matrix that is reading these dynamics, and then it's projecting to my output. And this matrix has weights, and what I will train is the weights of this output matrix. So this framework is called reservoir computing. In the traditional way to do neural networks, people used to train the connection weights inside of the recurrent layer. But it has been shown that it's very, very hard to train this. You need a lot of computation, a lot of hours to do that. And then some time ago, 20 years ago, someone had the idea of fixing the weights here and training the output weights. And it has been shown that it's much quicker and much simpler to train in that way. So this is called reservoir computing. What we did differently here is that the properties of this recurrent layer are based on what we see in the visual cortex. So this is fixed, and then we train that. So let's say this is my input, this is the desired output, but the network actually generated this. So this is not what I was expecting. So I changed these weights in order to obtain the desired output. This is the training part. Once the network is trained, it gets so good at predicting the next point. So let's say I give the network a given frame, and the network is able to tell me what is the next frame. The network gets so good at that I can do a thing that we call closed loop forecasting, that I take the output of my network, and this is the input for the next time. So the network is no longer seeing the real movie, but is the prediction of the network that is being used as the input. Why we are doing that? Because we want to study a thing in the visual system that is called short-term prediction. So imagine that, and I know this is a North American example, but there is very famous. There's a thing in baseball that people call a curveball. So a curveball, when the person throws the ball, we have a curve, as the name suggests. And because of that, there is a visual illusions that a lot of players already reported that it's too fast. So your eyes, there is no time to process that. So your brain somehow needs to make a prediction where the ball will be for you to be able to hit it. How is the brain doing that? There's no time to process the visual input. So there should be some time of prediction that your brain is doing. So our model here with the closed loop forecasting is able to actually study that, because we are not seeing the input anymore, but only the network itself is generating it. So here I will show you what happens with the network after we train it. So this is the ground truth movie, and this is the forecast that our network produces, and this is the activity inside of the recurrent layer, and this is the forecast when we cue the recurrent connections. Let's say we just have a feed-forward network. It's just the input, and we train over just that input instead of having this interaction between the nodes in the recurrent layer. So let's see what happens. So that's the real movie. That's what our network predicts. That's the dynamics within that recurrent layer. And that's the prediction without recurrence there. What is happening is that without recurrence, the network is learning the average of the movie. So the movie is going up and down, and then we have this thing doing this movement there. Without recurrence, the network is only able to learn the average behavior. But with recurrence, the combination of inputs and recurrence there actually allow the network to learn correctly the movement there. So of course, that's a very simple case. because we want to study the visual system, we need to go to more sophisticated cases. So here, this is what we call a naturalistic scene. So this is the movie of a person walking, and then the procedure is exactly the same. We train the network to obtain the desired input, and by that, we change these output weights. Once the network is trained, we can perform the closed loop forecasting to study the short-term predictions in this network. So again, what I'm showing you here is exactly the same as before. The only difference is now that the movie is much more complicated than just a ball going up and down. So in this case, it's a person walking, and we can see that the network, when we train correctly with time delays and recurrence, is predicting perfectly. Without recurrence, again, I'm only learning the average movement of that person. And what is interesting is that when the network is predicting correctly, we have this combination of the input, but we also have these waves that are being generated over this input. And using the mathematical approach that I showed you before, we can actually show that this is a combination of those fundamental modes that are generating this activity in the network that is actually allowing the network to correctly predict this naturalistic scene. So this was one of the first examples that we had to show that this wavy, or this combination of these wavy dynamics is actually allowing the network to perform a sophisticated computation. Yeah, let me see. Okay, I still have time to show you these two other examples. So just to summarize what we have so far, I have this nonlinear system. And by the way, this was the dynamics in the previous example that I showed you. And this is reproducing the Kuramoto model, right? So this X has phase and amplitude, but the amplitude remains close to 1 because I have this nonlinear operator that is putting everyone back to the unit circle. And the phase is evolving between minus pi and pi in a non-trivial way. But what happens if we drop this nonlinear operator? If we drop this nonlinear operator, we can represent the dynamics in a closed form expression because the system becomes linear. So if I drop this, that's the equation that I get. For a given initial condition, all the future is determined by this equation here. What happens is that, obviously, we all seen the behavior of this type of equation. The amplitude now increases over time. And if the eigenvalues of this matrix are larger than 1, as time approaches infinity, the amplitude will explode. So we all know this network for being unstable. And it's true, in the asymptotic limit, the network is unstable. What we found, though, is that during transient, the amplitude doesn't explode, and the phase of this complex valued system evolves in a non-trivial way. So we can still see the main phenomena that we observed in the Kuramoto model that is nonlinear, we can still see in a linear system, but for a transient time. And the advantage here is that if we can use this to power our neural networks, we have a closed form solution. So this is the dream. We have now the analytical solution for the system. So let's see what we can do with this linear system now. So here we changed a little bit the setup of our network, but the idea is very similar. We have an input layer. We have the network that now I called CVNN, the complex valued neural network. We have the recurrent interactions there. And then there is a layer that is reading this interaction. Before it was that output matrix that I was training. Now it's just a simple decoder that is identifying the synchronization level of parts of this network. So now my differential equation is this complex valued linear one. And as I said, there is a closed form solution for that. We all solved this equation at some point of our lives here. And the interpretation is exactly the same. We still have a matrix that has the connectivity, the phase delay, and the coupling strength. So just to show you, even though this is a linear system, this is the behavior of one node in a network in the complex plane. So time is evolving here in color code. So we can see that instead of being that idea that we have in mind that is just a spiral that is increasing, it's actually doing some non-trivial things there. if we look at just the phase of this node, we can see that we even have different periods there. So it's not even just a very simple oscillation. And when we look at the amplitude, it's actually going up and down. So if I were to look at this behavior, I would say this is a nonlinear system. But this is actually the transient of a complex valued linear system. And the advantage here is, again, we have a closed form solution for it. So now I can write the output of a decoder, which is actually representing a computation in the network, in a closed form solution. So here, this is the decoder output. So let's say I'm going to that decoder, the decoder K. So I can represent this for every single step of time in a closed form expression. This is just a heaviside function just to have my output to be binary. This is an operator that is reading the level of synchronization of that part of the network. This is the dynamics evolution, which is given by this closed form expression, and this was just the initial state. So now I can represent what is coming out of my network in a closed form expression. What can I do with that then? So here the network is random. I apply an input, and this evolves to a state where when only part of the network is synchronized. So here we can see that the motion becomes coherent here, and the decoders that are reading this part, they line up, they are 1. The other part of the network are 0. So now I have a system that can identify this, where the network is synchronized, return number 1, and the other parts of the network will return number 0. And I can do that in a closed form expression. So for instance, I can instantiate logic gates using this idea. So I can calculate my x. In this case, we did an XOR gate. So I have my x, my y, and the z is just the decoder reading either 1 or 0. So I can calculate analytically what are the inputs that will instantiate my logic gate in the correct form. So here, when I have no input, the network has no chimera, there is no cluster of synchronized nodes, my output is 0. But then when I apply my x, which I calculate analytically, I know that the network will show a chimera because I have a closed form expression, so I know everything that will happen in my system. And then the decoder is number 1. When I apply only y, I also get a chimera, the decoder is number 1. But when I apply them both, these two things, they cancel each other, and I again have a number 0. So now I can instantiate a logic gate using the dynamics of this neural network in a closed form expression. I can also instantiate memory tasks. So I can calculate the inputs beforehand analytically, and then when I apply a given input to my network, I know that a chimera will appear in a given part of the network, in this case here. So the item that is being decoded is the item related to the position of that synchronized cluster. But the advantage is that because I have an analytical solution, I can do online changing. I don't need to compute anything over time because I have this in a closed form expression. So let's say now I want to go from input number 2 to number 6. I can do it in a very straightforward manner. I can also instantiate, for instance, message encryption. I can use the position of the synchronized clusters as represented letters of the English alphabet. And then I can have a pair of private public key. And then I have the traditional thing with Bob and Alice. Bob sends a message to Alice, and Eve is trying to intercept that message. But because I have everything in a closed form expression, everything is deterministic here. So I can do that in an analytical way, and I know that Eve won't be able to intercept the message, and I know that Alice will be able to do it. So here, for instance, I have a message that is being sent, and Alice just needs to run the network. When it runs the network, the synchronized clusters will pop up, and then the letters will be identified. And then again, I have a closed form solution, so I know exactly how the network is performing this kind of thing. And so in this case, it was a very simple message. And of course, this is just to show that it works. And we have now people in our group trying to push this even further to optimize, to do it more quickly, to do it in a safer way. And just to show you that, okay, so we have this neural network, we have this analytical description, we can design computations there, but why do I care? It's just a toy network. What can you do with that? So here what we did, with our collaborators they do intracellular recordings of neurons. We use a biological neuron to read the dynamics of the network, and then this biological neuron fires or not to represent a number 1 or a number 0. So this represents a thing that is an artificial neural network that is coupled with a biological neural network to perform a given computation, and still we have the closed form expression there. So in this case, we have this, this is the dynamics of the network. So we have this part of the network being inputted to a neuron, this part of the network to the other neuron, and so on and so forth. And what happens is that because this is the part of the network that is coherent, this will make the neuron fire. So what happens is that when we input the correct item being remembered, the black neuron fires. When is the part of the network that is not remembering that item, the neuron doesn't fire. And then we can use these spike patterns to decode what item is being held in memory. And when we do that over different files with different neurons, we can successfully decode what was the item that was being held in memory. So we can perform, we also did this for the XOR gate. We can also do that for the message. We can use a biological neuron to decode what is happening in the network. And just the final example that I want to show you is that using this linear complex valued neural network, I can also perform image segmentation. So again, I have the analytical solution for this network, so I can understand exactly how the network is performing that task. So the task is the following. I have this as my input. So there's a square and a triangle there. But this is a binary input. So the square and the triangle, they have the same value. So the network should be able to tell me this is different than that. And that's the task here, right? Because if I just input this in a feed forward thing, this will say, okay, this is black, this is white, and this is black. It's not differentiating the square and the triangle. But I want the network, through using the dynamics of this network, being able to differentiate these two things. So just to give you an example, so here we have an input that is a triangle and the number 3, and here the square and the triangle. And this is the phase dynamics of my linear network. So we can see that there are waves emerging there. And again, I know how to create the conditions for the network to have waves. So I can leverage that to perform these computations now. And we can already see that we can differentiate the background from the things that are in the foreground. So what we did, we implement a 2-step segmentation here. So we have our input. We start the network in random initial conditions, and then the background and the objects, they synchronize in different phases. So these I use to remove my background, and then I start my network again. And because of the connectivity that I use there, I know that different waves will appear to these two different objects. Because again, I have this analytical control. I know what is generating these waves. So now what I can do, I can analyze this phase dynamics here and do a phase similarity there. And this allows me to do a low dimensional representation of these dynamics. And with this, I can differentiate these two objects, which was white, black, and black. Now is white, black, and gray. My network is able, throughout its dynamics, to segment these two objects. And the cool thing is that, because usually what people do, the traditional way to solve this problem is that you show the network 1,000 examples. Different square, different triangles, you rotate the triangles, you put the triangles different places, you add a second square, and then you train your network, and then you show new objects. And then you hope that your network, the one that was trained, is able to identify this new case. That's the traditional way to think about this problem. But now we have the analytical understanding, so we can kind of use first principles. What we need the network to have different dynamics where there is a square or where there is a triangle. So we can design the network to do so. So usually what you need 1,000 examples to train your network or 10,000. Now we can use 2 examples to do first principles just to get the right parameters to get the dynamics that we want. And with this, with the same network, the same set of parameters, without training, we can get the network to segment this case, and this case. So very, very different cases. I don't need to do that extensive training anymore. I can use the insights of the dynamics of my network to do it. And that is answering part of the problem that I presented in the beginning. How the connectivity is supporting dynamics that is supporting computation. Now through the framework that we have developed, we know how to design a network to display a given dynamics, and now we can leverage that to do computation, and in this case, to reduce training. And the cool thing is that not only we can do it, but we can understand why the network is doing it. So in this case, the network, again, I have the input and the recurrent layer there. So these 2 things are combining. I have the input and the recurrent dynamics that is emerging there. I can, again, analyze the eigenvalues and eigenvectors. And what happens there is that when I have a square and a triangle, the top eigenvalues are actually representing this square and the triangle with the dynamics there. So here we have different phases for the square, the triangle. Those are the fundamental, and I know those are Fourier modes, but those are the fundamental modes here. When we combine these modes, we see the waves appearing and the dynamics happening. So what happens if I change and I put a square here? The eigenvectors will reflect that, and that's why the network will be able to do it. So now we understand the underlying mechanism for this system to perform image segmentation, and that's why I don't need to train my network like a black box. I put 1,000 examples, I train my network, and I test in 100 examples, and it works, great. If I change these parameters randomly, maybe I will improve by 5%. Who knows? Let's try again. In this case, the approach is completely different. I want to understand the physics that is happening in the network behind it, and then I know when it will work and when it won't work, and how this process is happening. So just to finish my presentation, and then I'm happy to discuss more. In the first part, I presented this approach that we developed to these oscillator networks to connect the properties of the connectivity and the time delays to the dynamics that emerges. With that, we have this unified view of this spatiotemporal dynamics using the eigenvalues and eigenvectors. We can have predictions of the dynamics in the case, even in the case with multiple time delays. And now we are able to use that to design neural networks to perform a bunch of computations. This is going from logic gates, memory tasks, message encryption, computer vision tasks involving the short-term prediction, and even the image segmentation. And not only we can perform it, but we can understand why the network and how the network is performing a given task. So we have this mathematical description of the computations in this type of network. So this is the end of my presentation. Thanks again for being here and for attention. Of course, as I said, this is a joint effort. I'm not the only one working on this. We have a lot of people working on this under different perspectives. Those are some of the collaborators. And if you're interested in this kind of research, if you have an idea that you want to discuss, please send me an email. We are always looking for new master students, PhD students, postdocs. So if you are interested in this type of research, feel free to send me an email or even to my supervisor. And yeah, I'll be happy to discuss more. Thank you again for your attention and happy to discuss.
Now we open for questions, but I think we don't have so much time.
My question, but how the last work that you showed us, the figures have like symmetry. This is a reason, or you could have a high symmetrical figure, maybe 10 or something high, or even
That's a great point. Yeah. So here, so we started with this simple geometric data set, so to say, because our collaborators developed this background to as like a benchmark for this test. But like in this example, for instance, we can use the same network to do the image segmentation in the geometric case, but also in this realistic image. Of course, it doesn't work for all cases because in some cases the background and the foreground, they are too similar, for instance. And then when we look at the eigenvectors, we can see that the eigenvectors are not able to differentiate these two things. So a fractal is a good idea. We never tried it. We are developing, we are writing a new paper now that we are using the same network to do segmentations in cartoons. So we have like it's in between the geometric background and the naturalistic image, but we have like more control there. So we are doing that there. The fractals, I'm not sure. I think it should work. If the background and the foreground are different enough, the eigenvector should be able to differentiate it. But that's a good idea. Never try it. Thank you.
One more question.
Robert, when you show the Kuramoto order parameter, you show a x in function of t. This can be a solution of any model or just is the potential of your capacitors in the brain of the patient.
So you mean this X here?
No, previously. The first time of you show the
I think the only time that I
no, so yeah.
here?
The one, yes, the x. What is
Oh.
the x?
So the X here is it's because we have the Kuramoto model that is described with by the phases by theta. My X is the state variable of the complex valued approach that we developed. So this variable here has phase and amplitude. And then we compare the phase of this approach with the phase of the Kuramoto model. And so we take the argument or the phase of this X to compare with the phase dynamics of the Kuramoto model. And in this case, we don't care about the amplitude because this lambda operator, it's making the amplitude always close to 1. In the second part, when we don't have this lambda operator, we actually have the amplitude increasing and we can use the amplitude as well to perform computations. We decided to focus on the phase dynamics because the phase dynamics is bounded for a longer time because it's always between minus pi and pi. So it was more stable, so to say, to perform computations, but you can use the amplitude in that case as well. Here, we don't care about the amplitude because it's always close to 1, and we always look at the phase of this X state.
Thank you very much.
Okay, let's thank again Dr. Brzezinski.
Thank you.